the notes. So, proof by induction. And so as we saw in 3.2 and the problem that I just went over, we were using induction to prove that closed form solutions of recurrence relations were actually correct. And then in 3.3, we kind of extended the idea of recursion to more general ideas. So essentially now what we're going to do is we're going to take induction and prove more general things with it. So we're not just going to use it on these closed form things. We're going to be able to use it to prove, well, not anything. There's going to be a lot more general things where we have this idea of getting from one step to another in a certain way, and we're going to be able to prove that those things work via induction. So, principle of mathematical induction: to prove the statement depending on n for all n greater than or equal to 1. Remember, again, we kind of just went over this by reviewing that example. It suffices to prove that the statement is true for some base case, which is usually n equals 1. And then to take that is true for some k minus 1 and show it's true for k. So remember, we kind of have those two steps, the base case and the inductive step. And we have to write the inductive hypothesis, of course. So say we look back at something that we go away a little. Oh, what have I done? It's okay. It's okay. I don't know what that did. Anyway. So in another section, we looked at the idea when we were talking about sigma notation. We found out that if you wanted to add up all of the numbers from 1 through n for any positive integers, it's going to be equivalent to n times n plus 1 over 2. So we want to show that this actually holds. We want to prove that this is true for absolutely any n value. And we're going to use that by induction, because again, with induction, remember, there's essentially infinitely many things. That's another thing that I saw in your exams a lot, is some of you proved that it worked for, a couple cases, and then you stopped, which, I mean, you couldn't go any further because you'd be there for 5 million bajillion years. But we can't just do proof by example. We can't just say, well, this works for 1 and 2 and 3 and 4, so it looks like it's going to work for all of them. Remember, when we were talking about induction before, we also got into those ideas of finding counter examples for induction. So for induction, you really do have to focus on that generic process of saying it's true for this base case, assume it's true for this generic case, prove the next case up is true. So say we wanted to prove this statement that the sum of all numbers, integers 1 through n, is equal to n times n plus 1 over 2. So first we need the base case. That's really thick. Base case. So notice we're working on n greater than or equal to 1. So essentially the base case is always the smallest case you're looking at. So we're going to prove it for n equals 1. So essentially what we want to prove, if I'm being super general, we want to go from 1 to 1. Now it's kind of silly to write that in sigma notation, but just to format it in the way that the problem is given, I'll write it like that. So this would be 1 plus nothing, so 1. But then we want to show that the other side also comes out to 1 as well. So if we plug in n equals 1 on the other side, we're going to get 1 times 1 plus 1 over 2. So 2 over 2 equals 1. So 1 equals 1. So our base case is shown. So we've done our base case. And now I got to remember to slow down a little bit. Starting to talk a little too fast. So we've proven our base case, and now we want to assume that it's true for some generic k minus 1 and show that it also holds for k equals 1. Now with these, as long as you have the process down in your head, part is the algebra. And that's, so you have to have the process down in your head. So as long as you have that in your head, then the hardest part is going to be the algebra, because with some of these, the algebra can look a little gross. But as long as you just take a step back, try to just slow down a little bit, should be all right. So next we need our inductive hypothesis. So remember, this is where we say that it's generically true for some k minus 1. And remember, the k minus 1, it doesn't really matter that it's k minus 1. You can make it whatever the heck you want. But it's just convention and everyone agrees, just assume it's true for k minus 1 and show it's true for k. Someone on the exam assumed it was true for n and then showed that it was true for n plus 1. That's perfectly fine. But anyway, so we're going to assume that essentially this thing that we're looking at k minus 1 is going to be true. So if we let n be k minus 1, we're going to assume that this is true. So let me rewrite that last side really quick. Actually, no, I think I'm going to want to keep it like that. I'm going to want to keep it. So I won't rewrite that. You know what? I'll rewrite it just in case you thought to rewrite it, but I'll also leave the other side. So say you had thought to take it all the way down here. We're not going to need it like that. We're actually going to want to keep it like this. But the simplification doesn't really, it's not really wrong as long as you remember that it came from the thing on the left. Whoops. And we should always say that we're assuming this for k is greater than 1. So remember, that's just like the generic setup of this step. You assume that that entire thing you're wanting to prove is true if that n value is k minus 1. And we need to look at our inductive step. So this is where we assume, sorry, we don't assume. We look at this thing that we want to prove in terms of k and try to use this assumption in the inductive hypothesis to get what we want. So let me write down what we want really quick. So we want to show that if we replace n with k, that is true. So that's what we're kind of working up towards. So also remember is you always kind of want to keep in mind the goal, because you want to see how you can manipulate what we have into what we want. So I'm going to wait 5 seconds before I move forward in case people are trying to catch up a little bit and wrap their brains around it. So what you want to do is you want to essentially start with the left side of whatever you're looking at. So we're looking at this. Now, I can think of this as 1 plus 2 plus 3 plus onward plus k minus 2 plus k minus 1 plus k. Like that would be an equivalent way to format that, right? Now, if you notice, what we have is we have 1 through k minus 1 showing up there as well. So essentially what we're going to be able to do is we're going to be able to take that entire piece that I've just underlined in green and replace it with essentially the red piece from the thing above. Also, the other way you can think about it, if you don't want to write it out like that, remember that we can also essentially, we defined these sigma cursively, if you look back a couple sections. So if you remember, we could also say that we could take this down to k minus 1 and then add on just that last value of k. And if writing it like that makes it easier to see that we can replace that with that red box piece, that might be easier. But essentially what we've done is we've taken what we want and we've essentially found the inductive hypothesis inside of it. So that's what you're kind of always looking for. You're looking for the inductive hypothesis to show up somewhere inside of the thing you have to prove is true. So what we're going to do is we're going to take that green piece and we're going to replace it with the thing that's inside the red box. So what we get, we essentially get k minus 1 times k minus 1 plus 1. I actually think we are going to use the simplified version. Who cares? And then plus k. So I've taken that entire green piece and replaced it with what was in that red box above. Anyone who is colorblind, red, green, lines versus box. Maybe I should stop using red and green. Now, we still want, maybe I shouldn't have that in green. We want this. We want k times k plus 1 over 2. So what we essentially need to do now is a bunch of algebra on this step that we just came out to try to make that happen. So I want to try to manipulate what I have into what I want. So the first thing I should try to do is, I notice that I have a fraction in the first term, but none in the second term. So why don't I take that second term and turn it into a fraction? So I could do that, and specifically I want to be strategic and say that I'm going to want this to be over 2 so that I can put them together. I'm going to need a common denominator. Also, I am actually going to go ahead and simplify that first term. I said we weren't going to need to simplify it. I lied. We don't need to, but anyway. So if I did that wrong. 2k over 2. Sorry. So I can turn k into 2k over 2. I'm essentially multiplying it by 2 over 2, which is 1, which is perfectly okay. And I don't know how fast to move because I can't see anyone's faces, so I don't know if anyone's like terrified or not. But so we're going to try to squish this together. So now that we have a common denominator, we can add these fractions together. I'm out of space. Let me also distribute this k through in that first term. So we'd get k squared minus 1 plus 2k over 2. Whoops. K squared minus k. Sorry, I didn't distribute it fully. So k squared minus k plus 2k. So we'd get k squared plus k over 2. Now here's where we're at, and I'll erase this arrow in a second, and here's what I want. So can I somehow manipulate that k squared plus k over 2 into some k times k plus 1 over 2? Well, I can do that by just factoring out a k. If I factor out a k there, and this is what I meant by the algebra is the thing that's the worst in these inductive, full induction proofs, is the algebra is really the hardest part as long as you have the process in your brain. But if I factor that k out, then I have exactly what I wanted. I've just shown that the sigma notation is equivalent to the proper other side, if you will. I've just shown that it gives me exactly what I wanted. So let me clean this up a little bit because now I've got arrows all over the place. I'll leave that boxed up there. It's not, so I understand what you're saying by it seems super complicated, but essentially the reason we need to do this is because we can't just necessarily say, oh, I think this is true, I'm going to go ahead and use this whenever I want to. So essentially we need to be able to have a way to prove that these things actually work, and this is just the unfortunate process that allows us to do so. So I understand that you would definitely just want to be like, well, can't I just use this because they tell me it's true? And yeah, that'd be great and ideal, but sometimes we need to actually be able to sit down and say, okay, but I need to prove that this is true. I need to prove that I can actually use this, and that's what we're focusing on right now. So we could say by induction, essentially what we have, I equals 1 to n of I, is equal to n times n plus 1 over 2 for all n greater than or equal to 1. So again, algebra can get a little gross here, but the reason we're doing this is because we have to show that this does actually work. And I know that a lot of people just want to be able to use math and not know why it works, but sometimes we need to say, we need to sit down and figure out actually why this works. Now, I know we're focusing on this in a very mathy way, but you can also think about it in terms of, you know, some types of code sometimes. Sometimes code, you know, it can somewhat be self-referential, not really, but, you know, it can refer to itself in steps. And so if you're looking at code and you want to show that it actually shows what you want it to do, you're going to have to prove to them that it does the steps that you want it to do. So that's kind of what we're doing here. We're saying, hey, this is true. And someone's saying, okay, well, prove to me that it works. And so we have to actually sit down and say, okay, this is why it works. And we have to use induction to do so. So, Any questions on that? Let me try to zoom out a little bit to get a little bit of, nope, kind of that whole thing in there. Any questions on that example at all? So it's the same process. Feel free to type your question as I'm babbling. So it's the same type of process that we were doing for those closed forms. It's just that now we're looking at it not just in terms of closed form things. We're taking anything and proving it by induction. I'll wait for like 5 more seconds. Then we'll do another one after a tiny bit of notes. Okay. So, template for induction. Inductive proofs generally follow the format of the last example. And again, this is what I was saying. If you have that process in your brain, if you have the steps and you can tell yourself, okay, my next step is to do this, then the hardest part just becomes how do I manipulate this with algebra to get what I want. So we want to verify the base case. Don't forget the base case. You're going to suppose as an inductive hypothesis that the property holds for an object of level k minus 1 for some k greater than 1. And then use the inductive hypothesis and the recursive definition of the object to show that the property holds at an object level of k. And again, kind of the point with writing the inductive hypothesis is you essentially want to take the thing you want to prove then and find the inductive hypothesis somewhere. If you can't find the inductive hypothesis, either you've done something wrong or you can't prove that thing by induction. So in terms of all the questions will be given, since they can be proven by induction, you should be able to find that inductive hypothesis somewhere. So say we want to prove this next thing, which is going to be a lot of things to write out. It's very gross to write out, but we're going to prove that this is true. So we're going to prove for any n greater than or equal to 1, if you have 1 over 1 times 2 plus 1 over 2 times 3 and so on and so forth until you get 1 over n times n plus 1, that's going to be equivalent to just calculating 1 minus 1 over n plus 1. So I'm going to wait like 5 more seconds in case anyone's still writing down that process. In case anyone doesn't have the printout or something. So, base case, we need to prove it for n equals 1. So let me try to keep that in there a little bit. So we got base case on n equals 1. So if n equals 1, you know, if we think about the thing that we're doing is we're essentially writing it up to this piece, but if we're just working with 1, then we just kind of get this of 1 over 1 times 2, kind of just this first piece that stems from that idea. And we want to say, is this equal to 1 minus 1 over 1 plus 1? So is it true to the other side of the equation? Well, 1 over 1 times 2 is 1/2. And here we'll get 1 minus 1/2, which is 1/2. I don't know why I wrote my 1/2 like that on the other side. So 1/2 equals 1/2. So our base case is proven. We then want to assume it's true for k minus 1. So we want to assume that we essentially get all of this crap all the way up to letting n be k minus 1. So we want to, so inductive, I'm going to just start saying an inductive H. I'm probably going to start abbreviating it as IH and then IS for inductive step. But we're going to assume all of that nasty stuff. So 1 over 1 plus 2 times 1 over 2 times 3 plus so on till we get to k minus 1 times k minus 1 plus 1. You could simplify that a little bit if you want. We're going to assume that that's equal to 1 minus 1 over k minus 1 plus 1. And again, you could simplify that a little bit. I'm going to leave it as k minus 1 for now, just so that we recognize that this was a k minus 1 step. And we need to say for k greater than 1. So we did kind of need this kind of What's the word I want? That's just like proof language that we need at that step. Is we need to assume that it's true for some k greater than 1, because we just showed that it was proven for 1. So now we want to say, assume it's true for something greater than 1 and show it's true for the next step up. So we've got our inductive hypothesis. Now we're on to our inductive step, which again, I'm going to abbreviate as IS because I'm lazy at this point. So what we want, you don't always have to write out what you want, but because we're still kind of working on learning this, I'm going to write out what we want. So we want all of this craziness all the way up to k is equal to 1 minus 1 over k plus 1. So we want to show that that's true. So essentially, we're going to start with the left side and try to manipulate it until we get to the right side. But think about what that left side can be written as. I can rewrite that. If I break up the end a little bit more, I can write it as essentially the k minus 1 piece. Whoops. And then that last piece with k, that should be a plus amount of times. So essentially, I've just taken this and all I've done is rewritten it so that this piece actually shows up when I write it down. That piece was always there, it just didn't look like it until I wrote it out. But essentially, once I break it up like that, I've found my inductive hypothesis. Again, kind of the point in this step is to take what you want, find the inductive hypothesis in it, and replace the inductive hypothesis with the other side of the inductive hypothesis. So we've found the inductive hypothesis. It's right here. I said I was going to stop using green. So that is exactly the right side of our inductive hypothesis. So what we can do is we can take that chunk and replace it with the left side of the, the right side of the inductive hypothesis. I think I'm getting my right and my left mixed up. So we can take that entire chunk and replace it with what it's equal to by the inductive hypothesis. So it's kind of like by the inductive hypothesis, this chunk is equal to 1 minus k minus 1 plus 1. And then we still have to have that last piece at the back. We can't just forget about that piece. It still has to be there. And now what we want to do, once you've replaced your inductive hypothesis into the thing you're working with, you want to try to take that and manipulate it, and manipulate it into what we want. So we want it to try to somehow turn into 1 minus 1 over k plus 1. We have the 1 minus already, so it's probably that last two pieces that we need to somehow manipulate to get the 1 over k plus 1. So, well, I should be careful with circling the 1 minus because the minus does have to stick to that second term. So maybe that we have the 1 already and hope that those last two pieces turn into the negative 1 over k plus 1. So let's try to manipulate those last two pieces. So if I wanted to do that, I would probably want to combine them together using a common denominator. So why don't we do the first thing of essentially taking this denominator here, and why don't we simplify that a little bit? So we'll get 1 minus 1 over k plus 1 over k plus 1. So all I've done is I simplified that minus 1 plus 1 in the denominator of that second fraction. Yep, okay. I think I'm going, oh my lord, I'm running out of space. It's okay, I'll be able to fix that in a second. So say we want to combine these two things together, we would need a common denominator. So looks like our common denominator would probably be a k times k plus 1. So we would need to multiply that second fraction by a k plus 1. Now we need to be a little careful with this algebra because of this negative here. So you can't just squish that together to get k plus 1 because of that negative in the front of that second fraction. So what this would turn into is 1. So think about this as 1 plus negative k plus 1 over k times k plus 1 plus 1 over k plus 1. So kind of take that negative up into that fraction, or else you're going to do the algebra wrong. So we'll get 1 plus all over k plus 1. We'll get minus k minus 1 minus plus 1, sorry. So that negative 1 and plus 1 are going to cancel each other out. We'll get 1 plus negative k over k times k plus 1. And then essentially that negative can come back out. One moment. Minus 1 from the inductive step, the minus 1. My purple block. You mean this thing that I just circled in red? Pointing to the blue one. Yeah, okay. So that entire purple block is equal to the thing that's purple, underlined in purple above. It's essentially saying everything, all of the terms up to the k minus 1 term. So essentially what I'm doing is I'm taking what we're saying that that's equal to and replacing that purple block with it. So sorry, I'm not just replacing that purple block with 1, I'm replacing that purple block with the 1 minus 1 over k minus 1 plus 1. Because that's what I'm saying in the inductive hypothesis, that that purple block is equal to. Hopefully that makes sense. Let me clean this up a little bit. So yeah, essentially, I'm taking the entire thing that I want, which is all of that giant hoopla from essentially using 1 to k. But then the thing that I know is true is I know that the k minus 1 hoopla, if you will, can be replaced with 1 minus 1 over k minus 1 plus 1. So what I do is I find that idea in the inductive step. Oh, I'm getting the hiccups, that's not good. And once I find that, I can replace it with what the inductive hypothesis tells me it's equal to. So I found that entire purple block, and I'm saying, okay, well, my inductive hypothesis tells me that this entire purple block is equivalent to 1 minus 1 over k minus 1 plus 1. So I can take that entire purple block and replace it with it, which is, with, oh my gosh, with what is now in that red box. So notice we're not actually done yet. Because, and here I've written too large and I've run out of space, so I'll fix it up before I post these on Blackboard. But notice that what I have right now has a k when I don't want it to have a k. And has a k in the denominator when I don't want it to have a k in the denominator. But what can I do when I have a k over a k? I can just cancel them out. So the k in the numerator cancels out with that k in the denominator. I get 1 minus 1 over k plus 1. And now that I take that last final step, it's exactly what I wanted. So I'll clean that up before I post it onto Blackboard at the end of class. But, okay, so this one, I know that focusing on all of this is a lot of stuff to focus on, and it's a lot of nasty notation. But essentially what we've done is we've said that if we have this format where we're essentially taking 1 over n times n plus 1 for however many n's we have, that it's going to be equivalent to just calculating 1 minus 1 over n plus 1. So we did it for the base case. So the base case was essentially just that first term, that 1 over 1 times 2. And that was equivalent to 1 minus 1 over 1 plus 1. We showed that those were both equal to 1/2. We assumed that it was true all the way up to k minus 1, which gets me that thing that I underlined in purple. And I say that that's equal to that piece on the right. Now that piece, again, is just, I'm assuming that's true. That's coming from nowhere else other than I can assume it's true for the point of using induction. And then what I want to do is I want to take that nasty notation again, but extend it up to the kth term instead of the k minus 1 term. Once I extend it up to the kth term, I want to take that and I want to find the inductive hypothesis somewhere. And so what I can do is I can rewrite that out. Since I went all the way up to the kth term, I can write it with the k minus 1th term and then plus the kth term. And then I essentially, so I did that in the next step. And then I took that k minus 1 terms and boxed it in purple. And we're saying that is my inductive hypothesis. So I can replace it with what I just said it was equal to. So we replaced it with what we said it was equal to. Once you're there, that's when the algebra kicks in. And you just need to try to do some algebra to get to what you want. So what we wanted was we wanted some 1 minus 1 over k plus 1. So essentially we had the 1 in the front, but we needed to manipulate that back to fractions to turn into 1 over k plus 1. And if we do a bit of algebra, if we found a common denominator and then grouped them together, and then we had to cancel out that extra k at the end, we did come out to what we wanted. Hopefully that makes sense. And yes, these do take a lot of practice. I'm gonna leave, you know what, no, I'll leave those underlined. I won't box them. And let me unbox that. Well, I'll do that. To try to make it, when you look back at it later, you can try to figure out where things were coming from. Are there any questions or concerns about that one? We're going to go over one more. So, Brennan, here's what I was thinking. And I probably shouldn't even say this because I'm not sure whether I'm going to do it or not. But what I was thinking is is that I wasn't going to include this section on the next exam because I've already tested induction on this last one. Not this full type of induction, but a type of induction. And then this type of induction would just show up on your final. Which then, how much more complicated is it getting before your final, I guess, is the question then. Not any more complicated, really. Well, okay, so the next one we're going to do is a tiny bit more computer sciencey, a tiny bit more computer sciencey than this pure math algebra mess. And then we have to talk about this thing called strong induction, which is a step above regular induction, but mainly in its induction hypothesis step. It doesn't get any nastier with the algebra or anything like that. Well, you're welcome. But again, don't quote me on that because I'm not entirely sure, but I'm pretty sure. But don't get mad at me if I go back on it. But anyway, so it doesn't get much more complicated than this because, again, the bulk of the complication comes in the gross algebra that we get here. As long as you're focusing on the steps themselves aren't hard, but the algebra can be pretty gross. But anyway, now I'm just babbling the same thing over and over again. Questions, concerns about this one before we move on to one that, again, is the tiniest bit computer sciencey, but not really. It's just because we're focusing on strings instead of numbers. So it's like barely computer science. All right. So, and again, I'll fix that up a little bit. I'll like make things a little smaller, so maybe I'll just leave it. It's not that bad. Anyway, so remember, it was on your exam, and in one of the last sections, we talked about strings and we talked about the reverse of the string. So remember, that's essentially if we have the empty string, the reverse of it is itself. And then if we have one or more symbols, this was actually right. I kind of freaked out before about it saying one. But remember when we were doing these reversals and we had to add in the empty string, that's what takes care of that. So it does actually follow for one symbol. It's just that you then have to add in the empty string to it because you have to be able to write it as a symbol and a string. So saying one or more symbols is fine, but it's just that if you only have one symbol, you need the empty string. But anyway, I'm just babbling. So remember, we were doing this, and when you have more than one symbol, so you have a string and a symbol, the reverse brings that symbol outside, leaves the string with the reverse on it. So let's look at an induction idea with this idea of reversals. So for the next thing, though, we're going to want to use a theorem. We could technically prove the theorem in the problem itself, but let's go ahead and just prove this separately so then we can just refer to it in the induction. So we're going to say if A is a symbol, then A reversed is A. And this is essentially exactly what I was just trying to babble about, is that we can do this when it's just one symbol. We just have to add in that empty string. So if we wanted to prove that this was true, we kind of did this before in one of the reversals in the other one, where remember, once we got down to this symbol, we had to write it as the empty string times that symbol. Because again, that rule only works when you can write it as a string and a symbol. And then that rule for our recursion tells us to bring the symbol out front and leave the string in the reversal. And then the base case of that recursion tells us that the reverse of the empty string is the empty string. And the empty string can always just be dropped because it's the empty string. So now essentially we don't have to do all of this hoopla when we want to be able to say that just a symbol reversed just that symbol. We can now just say A reversal is A. For a specific singular symbol A. For the other ones, we do still have to do that, recursion idea. So what we're going to do is we're going to prove that the above definition that was on the last page that I just scrolled past, we're going to prove that it works. So that is, we're going to prove for any n greater than 1 that the reversal is essentially exactly what we think it is. It's just the string written in the opposite order. So if we want to do this, we have to do this by induction because we're proving it for all n greater than 1. So we've got to start with our base case. So you start with n equals 1. Now n here is essentially the amount of symbols. So if we're working with n equals 1, we're only looking at one symbol. So we want to say, what is the reversal of one symbol? And I'm even going to put a 1 there just to be super clear. Well, by that theorem we just proved, this is just A sub 1, which is exactly what it should be from the thing we have above. A sub 1 reversal should equal A sub 1. And this is by that theorem. I'll put that in by the above theorem, I'll maybe say. And this is what I meant by we could have technically proven that just as the base case. We could have done the work that we did in the proof above as the base case. But doing it separately is just going to make this proof look a bit cleaner because we don't have all that work that we had to redo. So now we've got our induction hypothesis, which is to assume that this idea holds for some k minus 1. So we're going to take k minus 1 symbols and assume that their reversal is just that k minus 1 symbols written backwards. So we're going to assume That's some a sub 1, a sub 2, all the way up through a sub k minus 1. Its reversal would just be what we kind of expect it to be. The a sub k minus 1 times a, not times, but concatenated with a k minus 2 all the way down to a 2 a sub 1. Essentially taking that entire string and writing it backwards. And our little proof verbiage, we have to assume that this is true for k greater than 1. So now once we get to our inductive step, again, let me write down what we want. Again, you don't usually have to do this piece, but just to remind us what we're looking for. We're looking for all the way up to a sub k reversed to be equal to a sub k, a k minus 1, all the way down to a sub 1. So that's what we're looking for. So essentially we're going to start with that left side. We're going to try to find the right side. We're going to try to find it somewhere. So we're going to start with a1, a2, all the way up to ak, and reversal. So we somehow want to make this show up. The string of a1 through ak minus 1 reversed. Well, if I use that recursive step on what I have right now and take that a sub k out to the front, then what I'm going to be left with is that string from a1 to ak minus 1 all reversed. So by essentially, we can do this, we can bring that ak out front. And this is essentially by that recursion step from the definition above, which is why I wrote by R. And now this thing here is exactly our inductive hypothesis. So essentially what that's doing is that's saving us all the time of having to do, okay, then you bring out k minus 1, then you bring out k minus 2, then you bring out k minus 3, so on and so forth. So the fact that we have this inductive hypothesis to say, well, we already know what this is equal to, we can just go ahead and replace that entire thing that I've highlighted in yellow with what we already found it, what we were already assuming it to be, which is a k minus 1 all the way down to a1. This is exactly what we wanted. That's what we wanted that reversal to come out to be. So by induction, whoops. Come on, scroll up, scroll up. So we're already done this one by induction. For any, I don't think I wrote this last time, did I? I should have. So for any n greater than 1, if we have that string all the way up through a sub n, I ran out of space, this is going to be equal to just essentially that string written backwards. And this is kind of what I meant by the hardest piece of these is sometimes the algebra. Like this one, it seems like we didn't do a lot because there wasn't any algebra to do. All we had to do is we had to take one step to be able to make our inductive hypothesis appear. And once we found the inductive hypothesis, we just replaced it with what we had, and then essentially we're done. So with this one, there wasn't any algebra to make our lives terrible. But again, this is why you want to focus on those steps. Do the base case, assume your inductive hypothesis, then take what you want, find your inductive hypothesis within it, replace that inductive hypothesis, and if you need to, do any algebra. Otherwise, you should probably be pretty close to done. You might need to do a little bit of rearranging to actually see what you needed. But once you replace that inductive hypothesis, as long as this thing can be proven by induction, which again, all of the things we're working with should be, once you replace that inductive hypothesis, you're technically done. You just need to manipulate it a little bit to look like what you want. And again, so the main part with some of the more mathy ones is that the algebra gets bleh. I'm going to leave those highlighted pieces in there. Questions, concerns on that one? Okay. So we might be able to finish this then, which is good. So we need to talk about strong induction. So strong induction is a tiny step up from regular induction. That's why it needs to be called strong induction. So think about the Fibonacci sequence. So remember the Fibonacci sequence, the first two terms are 1, and then all the other terms come from manipulating the 2 terms before it. So in this case, the recursive step refers to 2 previous values of f, as opposed to the ones that we've already been working with that have only ever referred to the 1 before it. Like think about when we were talking about the recursive relations and the induction, essentially that you needed on this exam, the induction where we were just saying you have one thing and then you're using that one step before it to find your next term. So far, as I pretty much just said, so far in our inductive hypothesis, we've only referred to the immediately preceding case. So if we need to refer to more cases, like this idea of the Fibonacci sequence where we need to refer to 2, we're going to need to use strong induction. So the name indicates that we're essentially using a stronger inductive hypothesis. So again, the thing that really changes here is just the inductive hypothesis. The main rest of the process is the same. You're still doing a base case, you're still assuming a hypothesis, it's just a bit stronger now, and you're still using that hypothesis to prove the inductive step. So I'll wait for 5 seconds in case people are writing that down. We'll do one example of this and then we'll be done. So say we want to prove a statement that is essentially a statement depending on all n for n greater than or equal to 1. So it suffices to prove that it's true for n equals 1, so the base case, but then say that we're going to assume that it's true for n equals 1 and for n equals 2 and for n equals 3 and all the way up through k minus 1. So the difference here is that in the induction we were already doing, we were just saying assume it's true for k minus 1. We weren't assuming anything for anything less than k minus 1. But here what we're going to do is we're essentially going to say assume it's true for all of the cases between 1 and k minus 1. Assume that all of those are already true. And so we're not just assuming one thing is true, we're assuming a bunch of things are true. And then we can use that stronger inductive hypothesis to prove the step that we need to prove. I'm going to write this out in symbols. I don't know why I included this in the notes. Well, it's because I stole it from somebody else and she included it. But so I'll write it out, but I don't really like it. So statement. So we essentially assume that statement 1 is true and the statement. Thought you hadn't seen the and symbol in a while. There we go. And statement for 3, and then you keep going, and you assume that all of these are true up to statement k minus 1. And you're essentially showing that this implies symbol, that the statement is true for k. Again, I don't really know why I included that in there, but anyway. So again, the point here is that the difference is that we're not just assuming it for one case, we're assuming it for all of these cases. So now for the inductive hypothesis, we are assuming all previous cases are true, not just the immediate predecessor. Which is why this is called strong induction, because it's a stronger assumption to make. So let's see one example of strong induction, and then we'll call it a day, because I know, well, we're done. And then I know induction can be pretty taxing on the brain. So say we want to use strong induction to prove that every integer for n greater than 2 or equal to 2 is either prime or the product of primes. So we want to start with a base case. Again, the general process doesn't change. Base case, inductive hypothesis, inductive step. So we need to prove this for n equals 2. Well, is 2 a prime or a product of primes? So we'll say since the only factors of 2 are 2 and 1, 2 is prime. You shouldn't just say 2 is prime. You should give them some reason as to why you know that 2 is prime. So you should really say that piece of, since the only factors of 2 are 2 and 1, 2 is prime. Tell them why it's prime. So we've proven it for the base case. We need our inductive hypothesis, and I'll even write strong inductive hypothesis, but abbreviate because, again, I'm lazy. So strong inductive hypothesis. So we'll say let k be greater than 2 and assume for every I, now this is mainly, a lot of this is just the generic notation for the proof setup, so I'll explain it in a second after I write it out, is either prime or a product of primes. So let me explain some of that. The k greater than 2 is kind of what we were already working with. Remember when we were doing our inductive hypothesis, we always said for k greater than 1. Well, here we're working with n greater than or equal to 2, not k greater than or equal to 1. So that piece is kind of normal to what we were already doing. Whoops. But then this piece in here, for every I with I between 2 and k, that's the strong part. So that's kind of the new notation. We're essentially saying assume this is true for every single case between 2 and, sorry, it should be k minus 1. So assume it's true for 2 through k minus 1. So sorry, fix that really quick. I'll circle it in red so you know that I messed it up. So k minus 1. But that's the strong piece. We need to assume that it's true for everything from the beginning up to k minus 1. But apart from that, it's the same kind of ideas. We're assuming that it's true, so we're assuming that those things are either prime or a product of primes. So the only difference is kind of that piece in the middle where we have to say that it's true for all of the things between 2 and k minus 1. And then we have to do our inductive step. So essentially, we want to take some k and show that it's either prime or a product of prime. So let me write that down. So we want to show that k is either prime or a product of primes. And again, you never have to write out this want step, but if it helps you focus on what you're trying to get, go right ahead. So we kind of have two cases. If k is prime, we're done. Like if the k value you're looking at is actually a prime number, then that's it. It's a prime. So essentially the meat and potatoes of this comes from proving that if it's not prime, it is a product of primes. So if k is not prime, then essentially a greater than or equal to 2. Can you all hear me now? Oh, now I can't see the chat. Yeah, I'll definitely go back over what I just said. So apparently my office in the corner makes the Wi-Fi angry sometimes, so now I'm in the hallway. Okay. Oh, I hope I'm not annoying anyone. Let me run really quick over here. was I talking about? So if K is prime, we're done. I think that was said already before I cut out, but I'll just say it again just in case. So if K is prime, we're done because it's prime. If it's not prime, it can essentially be broken up into two factors that aren't 1 or K. So we have that K is equal to A times B for integers A greater than 2 and B greater than or equal to 2. And we can say that it's greater than or equal to 2 because we're something larger than 2, okay? Because we already showed that it was true for 2, and we're assuming that K is greater than 2. So essentially we can break it down into, two numbers that it's multiplied together to make. So if you think about what this inductive hypothesis is saying, it's telling us that any numbers that are less than K minus 1 but greater than or equal to 2 is either prime or a product of primes. So essentially that A and that B are either prime or a product of primes. So essentially by the inductive hypothesis, A and B are either prime or a product of primes. So K is a product of primes. Since, if A and B, say A and B are both prime in and of themselves, well then K is a product of two primes. Whereas if A and B are primes, well then K is also a product of primes, which makes it a product of primes. So essentially we needed this strong part here because we couldn't just assume that it was true for the one immediately below it. We needed to assume everything between 2 and K minus 1, specifically because we need to consider for absolutely any A that we get here and any B that we get here that it'll work for. So that's kind of why we needed this extra strong piece in here to be able to say for no matter what A is, no matter what B is, since they're less than K minus 1, since they're greater than 2, our inductive hypothesis holds. So thus, by induction, how do I want to phrase this? Every integer n for n greater than or equal to 2 is either prime or a product of primes. So again, the difference here is, I've already said it like 5 times, but we couldn't just assume it for the one directly below because we need to break it up into 2 separate pieces that can kind of be essentially anything at all. They don't have to break up into the pieces directly below it. So we needed to assume a bit more to be able to get there, but it's still going to work because if you think about this, building upwards, we started at 2, we showed that it was true. If we go to 3, well, that's prime, so we're good. If we go to 4, then it's equal to 2 times 2, so we're good because 2 is prime and 2 is prime, and continuing from there. So this still does work. Like, it still does do it in a somewhat step fashion, even kind of had to assume a bunch of things were true to be able to solve it. But anyway, so that's strong induction. The only difference is that we have to assume that it's true for essentially everything under what we're working with instead of just the one under it. Any questions, concerns about that? All right. So again, I'm thinking this type of induction isn't going to show up on your exam. The reason for that is we've kind of already touched upon it already. We've kind of already tested it. And I'd rather have kind of the newer content be the focus of the next exam that's coming up. Again, I'm hoping to have your exams graded by tonight. If I absolutely lose my mind, it might take by tomorrow, but you should have them up tonight on Blackboard. And yeah, otherwise, we're done 3-4. We're not going to talk about anything else in the last 10 minutes. It's not worth it. Your final is not optional. It is, you got to take it. It is cumulative. It is online because all of them are, of course. But we'll talk about that a bit more once we get there. Well, I guess if anyone has any questions they really want to talk about right now. But otherwise, if you feel fine, feel free to leave. If you have any questions, feel free to stick around for a second. Otherwise, I'll see y'all on Thursday. Oh, you probably want to know about your quiz, don't you? Let's see. Well, I guess, because the only thing we talked about is induction, is that your quiz is going to be on induction. Because that would make the most sense. Quiz. Let me think about it for a second. Yeah. We'll do an induction quiz. Sorry, I'm looking at something. Okay. So it will be the most similar to So I want to say it'll be the most most similar to example 1, but I don't think the algebra is as gross. So what I mean by similar is it'll be a similar thing where I have two things that I'm telling you are equal and you have to show me that they're equal, but the algebra shouldn't be as gross. So I'm trying to say that it's going to be more mathy than the string example, but not quite as horribly algebraic as 2. But it will be one question on induction for your quiz on Thursday. Don't panic. I'm going to try to make it as least algebraically gross as I can. Come in. But that's what it'll be. So if there are any questions, feel free to stick around. Otherwise, I'm done talking. So have a good day. I'll see you on Thursday. Yeah.